A permanent settlement on the moon is no longer a distant dream. NASA is studying how habitats, power systems, and resource extraction could create a self-sustaining lunar base where humans can live and work safely. Instead of building everything on Earth and transporting it, NASA's approach focuses on using local materials, robotic construction, and modular engineering. The goal is not simply survival, but a long-term community supported by energy, water, and protective structures, all designed around the moon's extreme environment. Understanding these early strategies reveals how humanity may eventually turn the moon into a permanent living destination. Designing a lunar settlement begins with understanding the moon's environment. The surface experiences extreme temperature swings, intense solar radiation, and frequent micrometeorite impacts that shape every engineering decision. Habitats must stay pressurized, shielded, and energy efficient while remaining easy to expand. Early prototypes show that modular structures, buried sections, and robotic maintenance will make long-term living more practical. These conditions explain why building on the moon is not about comfort first, but about environmental protection and sustainable operation. Securing reliable energy is one of the most important challenges for a lunar settlement. Solar power works well on the moon because there is no atmospheric interference. But the 2-week lunar night requires stored energy, battery systems, and diversified generation. Engineers are exploring large solar panel fields, underground storage banks, and portable rovers that redistribute power between modules. These early concepts show that electricity on the moon is not just for lighting and life support, but for heating, resource extraction, and continuous robotic activity across the settlement. Water becomes one of the most valuable resources on the moon, and recent discoveries show that frozen deposits exist in permanently shadowed craters near the poles. Extracting this ice will likely rely on automated drilling systems and heating units that separate water molecules from regolith. Once purified, this water can be used for drinking, agriculture experiments, and fuel production through electrolysis. These early methods explain why water management is the foundation of a long-term lunar settlement, supporting both human life and continuous robotic operations. Daily operations on a lunar settlement depend on coordinated robotics rather than constant human labor. Autonomous rovers deliver materials, monitor power grids, and repair exterior structures without exposing people to radiation or vacuum conditions. Inside the settlement, automated systems maintain air pressure, recycle waste, and monitor humidity, making each habitat module function like a smart building. Engineers expect that most construction, mining, and transportation will happen outside the habitat through scheduled robotic routines, supported by centralized controls. This approach reduces risk, saves energy, and allows the settlement to operate even when astronauts are resting or working indoors, showing why lunar living is designed around continuous automation. Protecting a lunar settlement from radiation and micrometeorites requires structural shielding beyond thin habitat walls. Engineers expect that many living spaces will be partially buried beneath regolith to absorb harmful particles and minimize interior exposure. Underground modules also maintain more stable temperatures, reducing heating and cooling demands across the settlement. Above ground, layered shielding and robotic exterior repairs ensure that domes remain safe without constant manual inspection. This protective approach makes lunar habitats feel more like interconnected underground districts rather than exposed surface buildings, showing how safety directly influences the entire design of a moon-based community. Transportation inside a lunar settlement must operate without open exterior walking, because the vacuum and radiation make routine travel unsafe for unprotected movement. Engineers are considering pressurized tunnels, cargo trams, and automated delivery pods that move supplies between living modules without requiring exterior suits. Outside the settlement, autonomous rovers will support long-distance travel, scouting new terrain, transporting regolith, and mapping safe construction zones. By combining internal pressurized mobility and external robotic logistics, a lunar settlement functions more like an underground campus with scheduled surface operations rather than a traditional town. These systems show that lunar mobility is designed around efficiency, safety, and continuous material flow instead of personal outdoor movement. Sustaining life on the moon requires controlled agriculture rather than traditional farming because there is no atmosphere, liquid water, or biological soil. Early lunar food systems are expected to use hydroponic trays and nutrient recycling units inside pressurized modules, relying on artificial lighting and consistent humidity. These experimental gardens can produce leafy vegetables, herbs, and small fruit varieties while also contributing to oxygen and humidity balance. Waste from plants and filtered water becomes part of a closed-loop cycle that reduces dependence on Earth supplies. Over time, larger underground agricultural sections may support continuous food production, making lunar settlements less fragile and more independent during long-term habitation. A permanent lunar settlement becomes possible when energy, shielding, automation, transportation, and controlled agriculture all work as a coordinated system rather than separate technologies. Each component supports the others. Power grids supply heating and mining. Underground shielding stabilizes habitats. Automation reduces exterior risk, and hydroponic food systems reduce dependence on Earth. These combined networks make a settlement feel less like a temporary outpost and more like a functioning community with continuous operations. Understanding how these systems interact shows that lunar living is not a single invention, but an integrated infrastructure that evolves step by step as engineering improves. Designing a city on the moon turns space exploration into a long-term engineering challenge rather than a short expedition. The technologies already being tested show how lunar settlements could evolve gradually, beginning with small robotic stations and expanding into underground communities supported by energy, automation, and controlled agriculture. As these systems mature, living beyond Earth becomes less theoretical and more like a new branch of infrastructure planning. Understanding this early roadmap helps us imagine how humanity may eventually establish permanent space communities built with practical engineering and continuous scientific progress.